Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. A racemic mixture is produced when a reaction generates a chiral center or centers without any stereo control, yielding equal amounts of R and S enantiomers. This happens when a prochiral phase is attacked equally from both sides. Option B. The starting material is cyclopentylene substituted with 2 methyl groups on the exocyclic carbon, specifically cyclopentylene dimethyl, i.e. 2-propan, 2-ylidene, cyclopentane, or more precisely cyclopentane with an exocyclic C is equal to C bearing 2 methyl groups. The alkene is CH3 to C is equal to cyclopentane, isopropylidencyclopentane. When Br2 in CCl4 adds across this exocyclic double bond, the 2 carbons of the double bond become sp3. The cyclopentane carbon, C1 of ring, becomes a new chiral center, and the exocyclic carbon bearing 2 identical methyl groups does not become chiral, it has 2 CH3 groups. Wait, let me reconsider the structure. It is cyclopentylene with H3C and CH3 on the EXO carbon, meaning the EXO carbon has 1 H3C and 1 CH3, 2 methyls, same, so it's CH3 to C is equal to cyclopentyl. Upon bromonium ion formation and ring opening, Br adds to both carbons. The EXO carbon gets Br and to CH3, that carbon is not chiral, 2 identical methyl groups. The ring carbon, C1 of cyclopentane, gets Br and is connected to 4 different groups, making it a new chiral center. Because the starting alkene is symmetric with respect to the 2 faces of the double bond, the molecule has no existing chirality and the 2 faces are enantiotopic. Br2 attacks from either face with equal probability, giving equal amounts of R and S at C1, a racemic mixture. Option A. The starting material already has a defined stereocenter, wedge CH3, and H2PT hydrogenation tends to proceed with facial selectivity based on existing stereocenters, substrate controlled, giving predominantly 1 diastereomer, not a racemic mixture. Option C. The trans 1,4 dimethylcyclohexane derivative with H2PD, the existing stereocenters, both CH3 groups defined by wedge dash, control facial selectivity of hydrogenation, giving preferential CIS addition from the less hindered phase, producing a specific diastereomer predominantly rather than a racemic mixture. Option D. The cyclopentene with defined stereocenters, H3C on dash at 1 carbon, CH3 on wedge at another, reacting with Br2, the existing chirality creates diastereotopic faces, so addition is not equal from both faces, giving unequal amounts of the 2 possible products, diastereomers, not a racemic mixture. Therefore, option B produces a racemic mixture because the symmetric exocyclic alkene lacks facial differentiation, and bromine addition creates 1 new chiral center with equal probability from both faces. Therefore, the correct answer is B. Therefore, the correct answer is option B.